Okay, welcome back to another fun and exciting video. Before we start on the worksheet, I just want to talk about confidence intervals in general. So we kind of have two types of confidence intervals. We have what's called a 1 proportion Z interval, or we have what's called a 1 sample T interval. These are our most important ones. Okay, and N stands for interval. So the way, I just wanted to explain like the basic concept of what's going on here. So we have this large group of people. There's a large group here, and I'm interested in something about this person, and I'm interested in a proportion. Okay, so I'm interested in P, which is the proportion from the population. But since the population is so big, we just can't go ask everybody in the population. So what we do is we take a sample, which remember the sample size is N, and we ask them all a question. So it's really, sometimes it's like a yes/no or question, or could be anything where we ask them a question and they give us categorical data. And then what we do is we add up all the successes. And then we take all the successes. So X is how many successes there were, so like how many yeses there were, and this is the sample size. And we take this number and divide it by this number. We call that P hat. So P hat is going to be how many successes there were over how many they asked. Okay, now this you can't have more successes than you asked, so this is always going to be some sort of a decimal. So what we do is we take that decimal and we add and subtract this thing called the margin of error, and then that's going to give us an interval. And the interval is going to have a lower and it's going to have an upper. Okay, and then this interval, we hope that the truth, this is the truth, we're hoping that the truth's in that interval somewhere. So we're basically taking a large group of maybe 5 million people. This might only be 200 maybe, and then from 200 people we're getting an idea of what's going on with the 5 million people. Same thing over here, you have a large group, and we're interested in these people, but in this case we're interested in the true average. So this is mu, that's the truth, it's the true average. But since there's so many people, we go ahead and take a sample. We take a sample, okay, and the size of that sample is N, but this data here is quantitative, it's like number based. So it's quantitative, which we've learned already. So what we do is with the quantitative data, it's like number based, we get the average, and the average is called X bar. And what we do is we add and we subtract this thing called the margin of error, which we'll learn about, and then that's going to give us an interval. It's going to give us a lower, it's going to give us an upper. Now there's long formulas, or there's not long, but there's certain formulas that go along with this, but we're going to be using Statcrunch, and our hope is that this truth is in here based off the sample. So that's what we're going to be doing. Give me a sec. Okay, so let's go ahead and get started with the worksheet. So a point estimate, this is not due, so don't worry about that. Okay, so actually I'll go ahead and erase that real quick. Okay, so a point estimate is used to approximate a population proportion. So we're doing estimating a population proportion, and that's going to be our P's. A point estimate is a single value or point used to estimate the population proportion. It's the best, the sample proportion is the best point estimate. Okay, and the sample proportion is actually called p hat. So this thing is called p, a little hat around there. This is the truth. So this is from the population. This is from the sample. Okay, we can use a sample proportion to construct a confidence interval. To estimate the true value of the population's proportion. The true value is p. And we should know how to interpret such confidence intervals, so we'll get how to do that before. Okay? This is the same thing, a confidence interval. Is a range of values denoted by a CI. The confidence level, I'm on number 5 now, is denoted by a CL, is the probability, blah, 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 blah. I don't like that definition too much. So. Okay, so this thing is called a critical value. We just did critical values. I just made a video on it yesterday. Critical values is a number on the border separating simple statistics that are likely to happen from those that are unlikely to happen. Now last time I did it, it was a Z alpha. Now it's going to be a Z alpha divided by 2. And the alpha divided by 2 is going to be the right side of the tail. Okay. So now this thing is built into the formula of that thing I was talking about earlier called the margin of error. Now I'm just going to kind of put it here. E is going to be alpha divided by 2 times this formula right here, which is p hat, 1 minus p hat over n. So what we're doing now is just basically how do we find this guy. Even though Statcrunch is going to do most of the work for us, we want you to be comfortable with finding these critical values. Okay, so let's find some critical values. Let's find the cutoff for alpha divided by 2 with the 90%. Okay, so let's scan back up here and look at these guys right here. So the way this works is if you have, I'm just going to show you how the alpha is related to the interval. So the interval kind of looks like this, where this is 90%. So if 90% is in the middle, then this part right here would be 5%, and this part here would be called 5%, and all together, that gets me 10%. So this 90% matches with this 10%. This 95 goes with the 5, and the 99 goes with the 1. So if you ever want to find the alpha, alpha is nothing more than 1 minus the CL. Okay, so let's get started on this one. Let's find the cutoff for alpha divided by 2 with the CL of 90. If the CL is 90%, does that make the alpha 10%? Yes, that's true. If that's 90, then alpha is 10. Then what is half of 10%? You could get your calculator and put 0.1, that's 10%, divided by 2, and you end up with 0.05. Okay, so we need to find the alpha divided by 2 cutoff. Okay, so in this case, it's going to be the area to the right of the critical value. So we're going to have to go to our Statcrunch and go to our normal calculator. Okay, that's 0. This is 1. I'm trying to find where this is 5%. That's what I'm doing right now. Okay. I have to set up Statcrunch, or just I'm going to pause the video for a second. Okay, I'm back here on Statcrunch now, and remember we're trying to find the Z star trying to find this guy right here. That shade's 90%. And the way we did this last time was use the Statcrunch. For the Statcrunch, we want to go to a normal calculator. Sorry. Okay, I think I'm hitting too far. Top, there we go. Okay, so what we want to do is make this thing 0.05. And make this a greater than sign. Okay, that's a greater than sign because I'm shaded on the right side. So 1.645. 1.645. So this is 1.645, and that's a alpha divided by 2 of 0.05. Okay, what about 95? So if this was a 95, see if we can figure this out. That's a 95%. Then that plus that is 5%. So alpha is 5%. We want alpha divided by 2. So we need to take 0.05 and divide it by 2, which we get 0.025. I'm just going to put it in alpha divided by 2. So when we go to Statcrunch, all we're doing is changing this guy. Let me get rid of this. All we're doing right here, we need to change this to 0.025, which is here. .025 is 2.5%. Click it, 1.96. 1.9599. That's good enough for 1.96. So this one here, this alpha divided by 2. Okay, now if it's 99% on the inside, then alpha is 1%. Half of 1% is 0.005. So I'll let you guys do that one, but you should end up with 2.576. And here's the directions on it. Here's the directions on how to do it. Okay, so let's go over some notation. Let's go over some notation. Okay, these are going to be important that you know. Population proportion, P. Sample proportion, P hat. Sample size, N. Margin of error, E. And this would be Z alpha divided by 2. Okay, we are going to be doing these, and we'll talk about that in a second. We'll be doing this later with some of our examples. Okay. Let's get started on some of these examples. Okay, so in a survey, they asked this many people, and that many people said they favor sports. Find the point estimate. Now remember, when they asked you a question, they said, what's your favorite sport? So the person either said football or maybe something else, not football. So what they did is they counted how many people said football, and there was 287. So p hat is going to be 287 divided by 1024. So you chuck that into your calculator. Oh, there it is. No. So it's 287 divided by, 287 divided by 1024. Oh, well, that wasn't right, but just put that in your calculator and you'll get it. Okay, what's the critical value that corresponds with a CL of 80%? I'm not going to do this one, but I'll do this. If 80% is in the middle, then altogether that's 20%. So you need this shade. You need this shade right here to be 0.1, 0.10. Okay, so just go back to normal calculator and put 0.10 in that box to the bottom right, and you'll get it. Okay, next. Find the critical value. Alpha is 0.04. So if alpha is 0.04, we need to find alpha divided by 2, which will be 0.02. So you need to go back to your normal calculator, and this needs to be 0.02. The mean needs to be 0 and the standard deviation needs to be 1. That shade needs to be 0.02. So you guys could do that. Okay, so be able to do the steps with no notes. You have to be able to do these with no notes. Okay, from a Princeton market research poll in which that many respondents, okay, so the best point estimate is going to be how many honked. This is p hat. How many honked divided by how many they asked. Okay, use a 95% confidence interval to answer these questions. So this is how you do it right here. I'm just going to follow these instructions. So you're going to go to your Statcrunch. Okay, I don't need any of this stuff, but I do need those numbers right there. What you're going to do is hit Stat, go down to Proportion Stat, one sample. Okay, now the difference between data and summary is data would be you had a bunch of yeses and nos. Summary means they gave you all the yeses and no. How many said yes? So click on that. Number of successes, that's 1083. The number of observations was 2518. Click the confidence interval, and I don't remember what confidence level they wanted. %. So we want to change this 0.95 to a 0.9. You can put a 0, you don't need the 0, and that's all you need to do. And you hit compute, and it gives me it right here. It gives me the lower and the upper. So I'm just gonna, guess I'm not gonna drag it out. 0.41 to 0.45. So 0.41 to 0.45. I usually I round it a little bit more. This is interval notation. 0.41 less than or equal to p, less than or equal to 0.45. So that's the difference. Okay, and this is how you do the write-up. We are 90% confident that the interval from 0.41 to 0.45 contains a true proportion of drivers who honked, who would honk when provoked. I'll write annoyed because that's what they wrote. Okay, so that's how you do a confidence interval, and that's how you interpret it. Okay, let's do another one. This one's going to be written a little differently. I'm going to go bring my calculator back up because I'm going to need my calculator. Okay, good. Of 260 employees randomly selected, just going to lower it, from one company, 18.46 of them commute by carpooling. Construct a 90% confidence interval for the true percentage. The true percentage is P. Well, I don't know what P is, so we're trying to estimate it. Okay, so there were, I'm just going to write this up to kind of help me out. There's 260, that's my N, and my P hat, which is the percentage, is 0.1846. So now we're going to go ahead and bring up Statcrunch again. Go ahead and run through the steps again. Stat, proportion stat. No. Got a glitch in this system. I'm using my pen. I'll go ahead and use my mouse. Okay, one sample, summary. Same thing. Well, they say, well, number of observations. That's pretty easy because they asked 260. Now they say, well, how many successes? Well, if you look back at the problem, they never tell us the number of successes. They gave us a percentage of successes, but not how many. So we have to convert that decimal into a number. So we need to find 18.46% of 260. So you do 260 times 0.1846. That's pretty close to 48, so we could go with 48. So 48 carpooled. They wanted a 90. Get off hypothesis test. Let's go to 90. And boom, there we go. There's our lower. So 14.5 to 22.4. 14.5 to 22.4. An interval notation would look like this. 0.145 is less than or equal to P is less than or equal to 0.224. And the way you interpret it is that we are 90% confident that the interval from 0.145 to 0.224 contains the true proportion of people who carpool. Okay? Alright, now this is a little different. I just have to talk about this for a quick second. Most statisticians don't blindly go out and take sample sizes. You can see they took 260. We don't know where they came up with that number, but we always like to plan ahead. Now, if you look back at the definition of the margin of error earlier, the margin of error is how far the truth can be from the sample estimate with that confidence. So we always want the margin of error to be as small as possible. Let me just show you what the margin of error means. The margin of error, so this is going to be the estimate we get from the sample. This is going to be your upper. And this is going to be your lower. And we hope that P is somewhere in between these guys. This distance right here is your margin of error. Let me show you. This distance right here, that's your margin of error. It's the same distance to here. That's your margin of error. So we want this thing to be small, because when this is small, your interval gets smaller. And if your interval is smaller, we have a better chance of capturing the truth. So we always want this thing to be smaller. Well, a lot of times, we're going to do the second one first. A company might come out and say, well, we want to do a confidence interval, but we want the margin of error to be no bigger than 4%. We want to be really confident. Okay, we know this p hat is estimated from the past to be 12%, and then they say, find the sample size. So we know how many we need to pick before we go out there. Okay, so what this question is saying is, hey, let's be prepared. Let's know how many we want to take. And if the sample size that it's going to generate, we'll make sure our interval will be, our margin of error will be 4%, which puts our interval at 8% at most. We're going to be really confident we're capturing the truth. Okay? Sorry about that. Okay? So I'm going to show you how to do this. It's just, they do it right here. I'm just following these instructions. So you can follow the instructions very easily. Okay, so we're going to go to Statcrunch, and I don't need any of this stuff anymore. Let me clear them all fast. Okay, we're going to go to Statcrunch, get rid of this thing. This is the steps. You hit Stat, go down to Proportion Stat, one sample, but don't go farther. If you're going to go into your intervals, you're going to go here, but we don't want to do that. We want to go down here, right there. So now they're going to ask for some things. Well, how confident do we want to be? Let's check. Going back to the problem, we want to be 99%. So 99%. So change that to a 9. Target proportion. The target proportion is whether you know something from the past. Do we know something from the past? We know a p hat to be 12%. So we're going to chuck the 12% in here. 0.12. Now the tricky part's the width. The width is always double the margin of error we want. So you'll see, I'll put in 8%. You're thinking, well, where did the 8% come from? Well, they want the margin of error to be 4%. We'll double the margin of error. See, it says width is 2 times E. That's E right there. So make sure you go back and watch this a few times so you get it. So 438. 438. So the answer right here, the answer here is going to be 438. Okay, this is at a minimum. You could take more, but that's the smallest number that you could take. Okay, well, how about this one? This is a really small margin of error. That thing right there is small. So 96%, and we have a small margin of error. These are unknown. So p hat is unknown. Then what we do is we make up a target. Our target's going to be 0.5. That's just fixed. 0.5 is kind of like our worst case scenario. Okay, so I'm going to go here. So now 99. Let's make sure it's 99. Nope, 96. So we want to go to 96. We need to change our target. Let me get rid of this other stuff that might be annoying. Okay, since we don't know anything previous, the target needs to be changed to 0.5. Okay, now our width is going to be 1%. That's because our margin of error is 0.5%, so 2 0.5% equals a whole percent. 42,179, that's how many we need. So that would be the minimum sample size needed. Okay, let's do another one of these. Actually, you guys could do this one. It's just similar to number 5. This just puts context to it. So I'll just give you a little hint. This one, nothing is known about the target on this one. The target is 0.5 on this one. The width equals to 0.08 on that one. Okay, here's your target on that one. And your width is still 0.08. That's how you do that one. Okay, now let's look at this one. This just gives you the formula how to find a p-hat, which is called your point estimate. So to find the point estimate, you just have to find the middle of these two people. The middle of here and here. So it's just the average of the two. Divided by 2. Okay, to find E, if they give you an interval, you take the range, which is the upper minus the lower, which is how big it is from here to here, and just cut it in half. Remember that margin of error is always half of your interval size. So make sure you listen to that a few times. Okay, so now we're moving on to the next section, which is going to be confidence intervals for means. Now they have the Z's or T's. We're only going to be doing the T's. So the formula here, well, they have the formulas. You're going to take the average from the sample and you're going to add and subtract the margin of error. Okay, the margin of error, which we're going to be using StatCrunch, but it's T star times the standard deviation of the sample divided by the square root of n. That's the margin of error formula. Okay, so in this case, like I said at the beginning of the video, you have this large group. This is the population. We want to know mu. We don't know mu. There's too many people there. So we take a sample. And we calculate the average from the sample. That's the sample mean. Okay, and we call that a point estimate. So the sample mean is the best point estimate for that person. I'm not saying that X bar is mu, but it gives us the best idea of mu. As long as you take randomly also. You have to have a random sample. Okay, so let's see this. Mu is the true mean. It's the true population mean. X bar is the sample mean. E is the margin of error. Just like before, we talk about margin of error. We're going to take a sample. We're going to put the sample result right in the middle. We're going to calculate an upper. We're going to calculate a lower. The distance from what we found, the average we found in the sample, to what StatCrunch gives us the upper is called the margin of error. We want that to be small. Take more people, it gets smaller. Okay, this T star is this, which I'll show you guys how to use. It's very similar to what we did earlier. Okay, what is the student T? So we have the Z distribution and we have these T distributions. They have the same general bell shape. Has a mean of 0, just like the other distribution, but this one, the standard deviation varies more. It's bigger. Remember, the Z distribution always looked like this. It would be 0, and this was always 1. This is the Z distribution. The T could change. There's a lot of T distributions. There's an infinite numbers. Actually, they don't look that good. The T distributions, and let me just stop you there. The T distribution is basically define this guy right here. Okay, that's part of the formula. So that could be like a T distribution. It sort of looks normal. It's still centered around 0, but the standard deviation is greater than 1. And the standard deviation depends on the sample size. Okay? And here's your sample size. So when the sample size increases, this DF thing will increase. Let me get rid of some of this stuff. You have to read a little bit about these T's, but they're very similar to the Z's. but you have this DF, and the higher the DF, the less variability in the T's. It means closer to a Z. Okay? And you'll see how to use it when we get to it. Okay, so determine sample size, we're going to do that, we're going to do this. So let's go ahead and do a problem like this, and I'll kind of show you how it works. So the T's are like the Z's, they're normal, but they're centered at 0, but their variability depends on how many you pick. So if you take 15, then the DF is going to be 15 minus 1, which is 14. So we need to go find a T that has a DF of 14. And then we use the same process we used earlier with this. If this is 95 in the middle, then this thing over here is 2.5%. Okay, so let me go ahead and show you how to find this. Okay, so before we used the Z calculator, now we're going to use the T calculator. T calculator. Let me move it up. Let me get it down here. Okay, so the T calculator, we need a DF of 14. The DF is always one less than the sample size. We want to make this a greater than sign. Now this red here needs to be 0.025. So we go 0.025. I got 2 decimals again, and compute. So 2.14. So this is 2.14. Okay, now we have a 90% interval. So this is 90%. So our goal is to find this percent right there. Or if this is 90, outside of 90 is 10, so this must be 5%. Now we have to find the DF. A sample size of 11 has a DF. Sorry, sample sizes of 12 has a DF of 11. So we could do the same thing. We just need to go back to Statcrunch. Get this out of the way. You can see it down here. I need to go to a DF of 11. And this right side needs to turn into a 0.05 for 5%. Compute. So that's 1 point. I'm just going to put it at 1.8. So the answer here is 1.8. Okay, I'll let you do that one. Okay. Now let's go ahead and find an interval here. Okay, listed below are the weights of randomly selected girls at birth. Use the sample data to construct 95% confidence interval for the mean birth weight of girls. So we're trying to figure out, hey, what's mu? Now the average of these is called X bar. The average of all girls is mu. So we're trying to use this 15 babies' weights to try to estimate this mu. Okay, so now like I said earlier with proportions, it's like yes-no type of situations. In this case, they're not yes-no type of situations, they're data, like the real number-based data. So I'm going to go ahead and clear these annotations, and what we need to do is open Statcrunch. Okay, we need to open Statcrunch and put the data in Statcrunch. Now, I'm not going to be able to see Statcrunch, so I have to move this out of the way, out of your view. And then I'm going to be putting them in now. Okay, good. I have all 15 in. Now let's go ahead and run the interval. Let me get rid of this guy. To run the interval, we want to hit T-stats. One sample. Now in this case, we actually have the data in. So we're going to click data. If we didn't hit the data, we would have been hitting stats. Select which column you have the data in. Come down here, click off that. And we want to find a 95%. So I'm already defaulted 95 and compute. And we bring this in, raise this up. Okay, so I think we can see both now. We need to do my interval is 29.24 to 32.5. And then say we are 95% confident that the interval from 29.24 HGs to 32.49 HGs contains the true, not the sample, the true mean girl baby weight. Okay, so that's how you do an interval like that. So you could run through that a few times if you'd like. Okay, let's do another one. A laboratory tested 12 chicken eggs and found that the mean, so I'm looking for like kind of keywords. Mean cholesterol was 185. That's from the sample. S is your standard deviation. Okay, so we could go do this. Okay, so we're going to go stat, T-stat, one sample. Now in this case we don't have the data. The data would mean we would have all the cholesterol levels. We have summary of the data. Sorry to click back and forth on you, but okay, so sample mean. Hopefully this doesn't go away. Okay, it went away. I'm going to pull this aside and then put it back. So my sample mean was 185. My sample standard deviation, you can see, is 17.6. And this size was 12. Now if you're not sure where the 12 came from, it's right here. They tested 12 chicken eggs, so that's your sample size. So, right there, and compute, so 173 to 190, 174 to 196. 174 to 196. So 1 174 to 196. And I'm just going to say it, you could write it. It's we are 95% confident that the interval from 174 to 196 contains the true mean cholesterol of all chickens of this type. Okay. Okay, so I'm going to give you an example of how to find the sample size before we do a study. Okay, so a consumer advocate wants to collect a sample of jelly jars and measure the actual weight of the product. He needs to collect enough data to construct a confidence interval with a margin of error of 2, so that he doesn't want the margin of error to be bigger than 2. So eventually when he gets his interval, whatever mean we end up getting to the upper, this distance right here cannot be bigger than 2. So that's going to be 2 or even less. We want to be 99% confidence. We want a 99% confidence level. The sample standard deviation from previous, so we know the sample standard deviation from previous has been 4. What do you recommend on the sample size? So this is just the same thing as before, but we're going to go to T-stat, not Z-stat. So what we do is we go to T-stats, one sample, and we go to width. Move this out of there. So we got 4 boxes again. In this case, we want to be 99% confident. This is standard deviation, which is right here, 4. Okay, now the width could be a little tricky, but the width is going to be, okay, so the width is going to be double the margin of error. See, let me show you how it works. I have a nice picture right here. So if this could be 2 at most, then the distance from the sample result, which we don't know yet, to the upper is allowed to be 2. So this is allowed to be 2. Let me change the color. This is allowed to be 2. And this is also allowed to be 2. For a total of 4. That's why your width is 4. These two 4s here, this 4 in the width and the 4 in the standard deviation, they're just the same because it's a coincidence. So you hit compute and they give you the recommended sample size of 31. So when you give this recommendation, you'd say n equals 31, or you could even do more. 31 is just the lowest you're allowed to take. Okay? Alright. Now in class I didn't go over the second part, but I'm going to go ahead and go over it now. So we do have an instance where means could be used. Means could be used as a z-stat and not a t-stat. It happens very, very rarely. I'm going to say that again. Means might not be t-stat, they could be z-stat. Okay, so we did this previous, so you gotta look at this earlier in the video. It's the same thing. But choosing between the student T, which we call this T-stat, or the Z distribution, which we call Z-stat. These are StatCrunch commands. Okay, conditions. Sigma is not known. Remember, sigma is the SD of the population. So if that's not known, and it's normally distributed population, or if sigma not known and n is greater than 30, you would use this T distribution. You could put an equal sign on that too if you want. Okay, what if a sigma is known in the population distribution, or sigma, we would use the Z. So the only difference between these two is sigma is known versus sigma not known. Okay, and I just want to show you something real quick. Now, that's a standard deviation. So students get a little get a little confused when they talk about standard deviation. I want to look at this laboratory rat problem. So the question is this standard deviation, is this sigma or is this S? Well, I mean, it says S. The standard deviation from the 12 eggs. This 17.6 is from the 12 eggs. So when you scan down and look at this, was sigma known or was sigma not known? And the answer is sigma was not known. If sigma was known, they would have used sigma. But since sigma was not known, they used S instead. So if you ever see an S, it's always a T stat. Okay, as long as, this last one's not true. If the population is not normal, it's not normally distributed, you can't do it. Okay, we need normality. To do a T-stat or a Z-stat, we need normality. And we did a condition earlier where if this is not met, then you can't do either of these. Okay, so let's try to see if we can figure this out. I'm doing problem 5. The variable under consideration is normally distributed. Perfect. If it's normally distributed, we could use the T or the Z. We could either do a T-stat or a Z-stat. Okay, in this case, but sigma is unknown. Sigma is not known. It's a T-stat. I'm calling it T-stat. They want you to write T distribution, but you should know it as a T-stat because that's what you're going to be hitting in Statcrunch. Okay, the variable under consideration is close to being normally distributed. That's good enough for normal. The sample is 75, and sigma is known. You're going to use a normal distribution, which is a Z-stat. Okay, this is going to be the same thing. The variable under consideration is not normally distributed and the sample size is 15. So when something is not normally distributed, your sample size has to be 30 or more. In this case, it's not 30 or more, so it's going to be a neither. Okay, it's able to use a T or the normal Z and then find that. Well, we've already found these before, so I'm not going to run over those again. But this is the T calc. And this is the Z calc. So you could refresh on how to do that. Okay, they give you a confidence interval. N is super small, but it's normally distributed. So since it's normally distributed, this is okay. Remember, if it's normally distributed, you can do any size. That's something we've learned in the past. Now, sigma, that's the standard deviation from the population, so it should be a Z. Z stat. Okay, now, population appears to be normal. So we're good. N is 17, but sigma is unknown. Since it's unknown, it's going to be a T, or T stat. Okay, so let's go ahead and run through these. Now this would be good because we're not going to know which one they are going into it. Okay, random sample of 104 light bulbs. So I'm kind of keeping track here. That's N. N is 104. Has a mean life of 543. Assume that the light bulb's normal life is normally distributed. Good, we're normal. Sigma is 26. So sigma is known. So we want to do a Z-stat, not a T-stat. I promise this is something you want to put a little time into and study. Okay, so let's go ahead and run the interval. Okay, so I'm going up here. Let me get rid of this stuff. I'm going to keep this stuff because I need to be able to see it when I'm putting the stuff in. So I'm not running back and forth. So we want to do stat. Z-stat, because sigma was known. One sample. We don't have the data. We have a summary of the data. Sample mean, that's 543. That's the average of the ones we tested. The standard deviation, which was given at 26, and our sample size was 104. Change it to here. I did forget what confidence they want. 90. So check off the 95 and compute. So anywhere from 538, 539 to 547. Okay, 539. Just move this out. No, I can't move it out. Okay, 539, 547. Okay, so the interpretation is we are 90% confident that the interval from 539 hours to 547 hours contains the true mean life mu of all light bulbs of this type. Okay, so you could rewind it and set that up. Okay, how many women must we randomly select? So this is a finding n problem. And all these StatCrunch commands are right here for you. We want 90% confidence, the sample to be within 3.4, so that's your margin of error. And the population standard deviation, so since they said population standard deviation, that's sigma, and that's known to be 25. Okay? So this is going to be a z-stat, because sigma is known. Alright, so let's go do this. What we want to do is hit stat, z-stat, one sample and width. Okay, now let's talk about some things that we need. What was the confidence? 90% confident. So we want to get rid of that. Boom. Standard deviation was 25. I thought it was 26. Let me do a quick look. 25. Okay, the margin of error is 3.4. So, since they want to be, whatever we end up getting for the mean to the upper, they want that to be the biggest at 3.4. So the width is going to be double that, 2 3.4s, which is going to be 6.8. And voila, 147. So this is no decimal. 147. Okay. Okay, for the following problems, find the confidence interval for the population mean. Decide whether it's a z-stat or a t-stat. Okay. A football coach randomly selects 10 players. What you need to ask yourself is, does they give you sigma anywhere? That's it. It's the standard deviation of all players. I don't see it anywhere. So in this case, it's going to be a t-stat. Okay, now to find the interval, we need to put all these values into the calculator, into StatCrunch, and then find the interval. Okay, I went ahead and just put them in there. I put them in variable 2. Don't need this anymore. Okay, I don't need this anymore. Okay, and variable 2, remember we said this was a t-stat, so I'm going to hit stat, t-stat, one sample, and we have the data here. So with data, I click variable 2, because that's where I have my data at. This, do quick check of the confidence level, 95%. So 95, and compute. So 8 to 11, essentially. There's your answer. So the answer is B as in boy. Okay, 37 packages are randomly selected from a packaging facility by a parcel service. The sample has a mean of 10.3. So always keep track of that. Since this is average from a sample, 10.3. And a population standard deviation of 2.4. So that's what I'm looking at. Did they give me this? Yes, they gave me that. So that's a z-stat. Okay, and n is 37. N is 37. And we get a 95% CI. So this is a z-stat. I have all the info that I need right there. Get out of this. Let me just erase this real quick. Now we want to do stat, z-stat, one sample. We don't have the actual data. We have a summary of the data. Sample mean is 10.3. Sample standard deviation is 2.4. And the sample size is 37. That's how many they looked at. Confidence level 95. Click on that and compute. So 952 to 11. And that's where we're at. Okay, and let's see if there's anything else down here. Okay, so that is it. Make sure that you spend some time on this stuff and watch it. Go slow. You should be spending about 3, probably to 5 hours on this video. Just going through, looking at things and seeing how thing works. So, and make sure you check the solutions for how to do the homeworks also. Oh, thanks for watching. Hopefully you made it to the end.